Hey, everybody.
Hi, Tom.
How you doing, Don?
Unfortunately, the last few hours I've been at a meeting,
Oh,
and I've been killed trying to get MCell to run on my computer. Um, I sent
oh,
Adam. I sent Adam the problem. The problem I'm having on the Windows computer, Windows 10, is it comes up and it says the configuration for the side-by-side configuration is incorrect. That's what it says.
huh. Never heard of such a thing.
I don't know what that means. So
No.
I did get it running at the SOC machine when I was at the machine, but I can't run it from home.
Right.
And George tells me it's because my operating system isn't good enough. He has an old operating system on my computer and he's never changed it in 5 years.
Oh, I thought it was supposed to be Windows 10, though.
No, this is the work computer
Oh,
on the net. Yeah, it hurts. Anyway, don't want to bother you about trivial things. The job, you're doing a great job. It's wonderful today. I was here
Thank
all
you.
morning in the morning.
Thank you. Thank you.
Good, Adam, yeah, you're doing just incredible.
Thanks. Yeah, I guess I was a little bit frustrated by that icosphere subdivision problem. I did a search on the internet about it, and nothing comes up. So I'm still scratching my head.
Really weird, especially when yesterday it worked. And
Yeah, I did it. I was up till, I don't know, like midnight last night, making going through it again and making those milestone files that you have there. And everything worked. And then, yeah, I don't know. But that's the only thing that's not working. So I guess we can be happy that there's not more things going on.
Adam, did you get my email about my
yes,
difficulty?
sorry, I just got to it just recently.
Yeah. Do you have any ideas about the side-by-side configuration?
And so this is on Windows 10.
Yes, sir.
It's a good one. Never heard.
Okay, yes, I found something based on Googling.
I mean, it's always possible I did something wrong and, didn't get everything loaded properly when I unpacked it or something. I don't know. But
Could you try follow or install the Visual C++ redistributable package? I don't know if you tried that.
say it again, Adam. I'm sorry. I just quite
I
get it.
send a link to chat.
Yeah.
And
Okay.
there's the section.
What do you want me to send the chat? The error message?
Yeah, I send a link to the chat and there's
Okay.
no to the Zoom chat. I sent a link.
Okay.
This seems, at least based on Googling, this seems related. Yeah, but this is for Blender 2.79. But
2.39.
yeah, I don't know. I would try to install this the package as is this described in the documentation and the link I sent, and you will see afterwards.
Okay, don't worry about it. Thank you very much. You guys got a bigger.
Okay. Guess we'll maybe wait one more minute. But while we're waiting for a few more people, so how's everyone doing? Can we see some thumbs up or thumbs down for how you're doing? Okay, people are generally happy and making things work. Okay, good. I was worried that I was kind of thrashing around a little bit there in the middle of things there, but I think we're past that now. So we're in the home stretch for making this model. Okay. So I will start sharing my screen. Looks like we're down to 22 people on board, so it's not quite as many as we had before, but let's keep going. Maybe people are frustrated and not coming back. I don't know. We'll see.
It might be also the time difference.
Yeah, it might be the time difference. Yeah. Okay, and let me get my chat up so I can see what people are saying. Okay. Stretch my chat. No. Bigger. Okay. So people should be at this point, and if not, you can load the milestone 2.5 to be right here. Yeah, UK probably due to current heat wave. Oh boy, so I didn't hear about the heat wave in UK. Yeah, above 45 and 50-degree latitude this year, man. It's pretty bad. It is pretty bad this year. I don't know what's going on. I guess we can call it climate change. Okay, so what we're going to do next, see if I click in here and make sure everything's live. What we're going to do next is add a second organelle, and I'm going to keep organelle. I'm gonna keep the compartment called site. I'm gonna keep that invisible for a moment while we add another icosphere. So let's go to the model objects panel and click on the icosphere constructor again. And this gives us a new icosphere. And again, this control panel here is grayed out and doesn't work. If it were, we'd be able to change the subdivisions and set the radius and the location all in one smooth motion over here, and it's grayed out. Even though I can move through it, I can't click on anything here. It is the craziest thing I've ever seen. I really don't understand it. Okay, enough frustration. So we'll go to the item control panel. And like last time, we'll change its scale to 0.2 this time. So 0.2 by 0.2 by 0.2. And our cheat sheet, where'd my cheat sheet go? There it is.
Okay, I found something for the icosphere.
Okay.
The global undo will be enabled, so it got lost probably somewhere during the.
Oh, that's crazy. I thought we had set that. Okay, so let's. I'm gonna delete what I just did, and I'm gonna go into my edit preferences, and the global undo is in the system. Huh. How did that get unchecked? I think we all set that earlier today, didn't we?
Yes.
Okay. Well, okay. Check global undo. Another good reason to have that checked. Okay. With that checked, I'm going to save my model. And I'll go back into CellBlender again. And in the model objects panel, and I'll say add an icosphere. And now it's not grayed out. Yay! I can increase the subdivisions of this guy, set its radius to be 0.2. Our cheat sheet says radius 0.2 and position R of Y equals positive 0.3. So if I come back over here, position, location Y, positive 0.3. Okay, so now we have what looks like a nice smooth sphere, much smoother with just with 3 subdivisions. So what does this mean? What does the subdivision mean? What it means is we start with an icosahedron, which is a 20-sided object. And we subdivide it one time would mean take all 20 sides and subdivide them along their edge, along the edges one time. So if you subdivide a triangle along its edge one time, so let's zoom in here for a moment. And here's a triangle. You can see that if I subdivided the edges of this triangle one time, here, here, and here, and made a triangle there, I would subdivide the whole triangle into 4 subtriangles. So every one subdivision adds another factor of 4 triangles. So if we go from 20 to 80, and then from 80 to 320 for the second subdivision. And then the third subdivision, but I think their counting doesn't. Let's see. Let's go down to 1. So 1 subdivision means it is an icosphere. So there's your icosphere with 20 sides, and then 80 sides, and then 320 sides. And if I keep going, I can get to very large numbers of triangles pretty quickly, so be careful with that. So the speed of a simulation in MCell is dependent mostly on the number of diffusing particles and partly on how many triangles are in the model. And I'll show you a way to kind of beat down the complexity scaling in the number of triangles and molecules very, very, very soon. There's an adjustment under this partitions panel here that lets us beat down the effect of that of the complexity of our simulation. But still, it's going to scale kind of linearly in the number of diffusing particles. Even beating it down. So we can't beat that completely out of the system. Okay, so here's our icosphere that we just added. Let's change its name to O2V, sorry. O2V, like that. And then add it as a model object. Oh, I can see somehow I lost my compartment names. Maybe when I was playing around with things, trying to fix the subdivision problem after during the break, I may have done something that screwed that up. So I'm going to type this in again for O1V. And remember, it was O1M was its membrane compartment, and then O2V. We're going. Its parent is site, and its membrane is going to be called O2M. Now we haven't made it yet. We haven't made that membrane yet, or named it yet. But we can specify it here or refer to it here Okay, and now what we can do is go into edit mode again. There's our object, and define a new region on O2V. And we're going to call it O2M. And we're going to assign those faces to it. And if we're ever in doubt about whether the assignment worked or not, we can click outside the object to unselect its faces and then say select, and then there they are, and then we can say deselect and they go away. There we go. And these buttons down here that let us assign, remove, select, and deselect, and select all these operations here only appears when we're in edit mode, which is indicated up here in the upper left-hand corner. And we can switch between object mode and edit mode with the tab key on the keyboard, or by going up here to this menu and selecting edit mode or object mode. Okay, so there's our object. And then the last thing we want to do to it is set a color for it, and then set its transparency to be 0.2 in the color properties panel here. And so there it is. And now at this point, we could make the site object be visible again so that we can see our whole model. So now this is the final geometry for our model. And then now to complete the model, or take it to the next step and then complete it, we are going to make some changes to the model. First of all, we're going in the molecules panel. We're going to add, well, let's go to the reactions panel first. So what we've done here so far is make kind of a toy model. I saw some discussion on here earlier about the biological relevance of this, but it's a toy model, but it's reminiscent or representative of lots of different kinds of cell processes, where we have cellular metabolites that are processed inside one organelle and segregated from the cytoplasm by the membrane of those organelles. And then you could have enzymes inside one organelle that process metabolites, and then other organelles where things are sequestered and degraded or processed in various ways. So this is a typical kind of thing that can happen in many cells. And these molecules don't represent anything in particular, but they could be replaced with with the names of real molecules and the kinetics of real molecules and the reaction pathways of real molecules. But what we're trying to do here with this model is kind of give you the awareness of the building blocks for how to build things in MCell and CellBlender and what's possible, some of the things that are possible, and there's a lot more possible with this. So I'm hoping that this model is complex enough to kind of inspire you, but a little bit, but simple enough to not be overwhelming in scope. Okay, so the next thing I'm going to do with this is, so what we've done so far is we've transported molecules of A inside here where they can react with the molecules of B that are sequestered inside here. And maybe in the cell, these B molecules are held in here because they're very toxic to other processes in the cell. And so the B molecules, whatever this is, needs to stay inside of this organelle. And but the product, the molecule C, that might be an important product to have distributed throughout the cell, or transported out of the organelle and used somewhere else. So let's write a new reaction where we're going to do exactly that. We're going to transport the molecules of C. So I'm going to say, C at in plus T1 goes to C at out plus T1 with a rate constant 1E8. Okay. So I'm keeping things simple and kind of repetitive here, because you learn well through, people learn well through repetition. Oh, and you can see I misspelled in there. Okay. We learn well through repetition, but it also helps me to have this, keep it memorized so I can teach it to you without fumbling about too much. And also, get these concepts kind of through repetition, kind of drilled into you a little bit. Okay, so C at in plus T1 goes to C at out plus T1. So again, we're using this in and out general way of talking about transport across any membrane in the model where T1 is present and it encounters the molecule of C. It'll do this transport in this direction from in to out. And okay, and so now adding that reaction, we'd be ready to run the simulation. And there's our result. And I can reload it. And now when I run the model, we can see that the molecules of C start appearing now in the cytoplasm. Molecules of C that were created inside start appearing in the cytoplasm because they're being transported by the T1 back out across the membrane from inside to outside. So the same transporter T1 in our model here, this same transporter T1 serves the purpose of moving A into organelle 1 or O1V and moving C out of O1V. Okay. And if we look at the plot from this, we're going to see, well, it looks the same, right, as what we saw just before, because all we've done here is we're creating C molecules and we've transported them across the membrane. But in the world, these are counts in the world, that transport doesn't change the amount of C that we've created. We've only, all it does is move it. Okay, so how do we keep track of where the molecules are and count those? So we can now go in here and I see there's some traffic on the Slack channel, people talking, but let me keep moving along here. So, so what we've done in our observables is we've counted A and B and C in the world. Let's count the amount of A molecules inside the object called O1V. So now this is going to track the rate of transport of A across the membrane into O1V. And if we look here, it says count A in or on O1V. And the in on means, if it's a volume molecule, it means in, and if it's a surface molecule, it means on. So we're just using a kind of a generic way of describing our observables here. This is just shorthand for what the, for what our selection options have chosen. And now let's count molecules of C in the object called O1V. And so now we're going to be counting C in the world, but also C inside O1V.
Sorry, Tom.
Yeah.
Could you please show again how to define the surface region? I
Sure.
prefer to show one step, to describe one step and.
Sure, absolutely, yeah. This is that's certainly something worth repeating many times. Okay, so and so we go to model objects. I'm going to hide. So this is something I don't like in this new version of Blender that was different in Blender 2.79. So if I select this object O2V that we want to say define a region on, we can see that it's there because I've done it, right? But if I go into edit mode, while this outer object is visible, I completely lose track of the object is selected. It says O2V. I can see everything here that I can assign and remove, but I can't see which faces are selected or anything in here. And it's because it's being hidden by this by the site object in Blender 2.79. You would still be able to see everything being selected in here, even with this visible. So I don't like this feature of Blender 2.93. Maybe there's an option somewhere to control that. But anyway, I'm going to get out of edit mode for a moment. I'm going to select the site object here, select it here, and then I'm going to hide it right there. And now when I select this and go into edit mode with the tab key, you can see there it is. If I hit the A key, it selects the whole thing. And then I could say assign. Well, I would hit plus to add a new one. Well, so let me delete it, right? And start again. So I'm going to hit plus to add a new region. I name the region O1M. I make sure everything's everything's selected on it that I want selected.
It should be
oh, thanks. Thank you, Adam. This should be O2M. Thank you. And make sure I have selected all the faces on it, and then I say assign. And then I could say deselect to deselect it, and you can see that only the edges are selected, but the faces have been deselected. So that indicates that I have successfully created this region. Okay, and then I can get out of edit mode and turn back on the site so we can see everything, and then there we are. And then I can save to make sure everything's up to date. Okay. So so back in the plot output, I added a count of C in or on O1V, and this one for C in the world, I might keep that one, but I might add another one for C, molecule C in the object called site. But I think that's not going to do what we want it to do here. So I'm going to delete that one, and I won't explain why I'm deleting it. But let's get rid of that one for a moment. That one's not going to do what we want. Okay. So we're going to count A in O1V and C in O1V, and C in the world and A in the world and B in the world. Okay. So now I'm ready to run this again. And there it is. And then in our plot, generate our plot. And now we can see that the molecules of C in the world is this line, and the molecules of C in O1V is this line. And then this one on the bottom is the amount of, are the A molecules in O1V. And we can see that the A molecules in the world are decreasing steadily, but the amount of A molecules in O1V is kind of comes up, and then it just kind of stays there because it's being consumed at a constant rate by its reaction with B. So the A is trickling in, and that reaction between A and B is fast enough that the concentration of A is kept low. And so this is confirming what I said before, that the limiting factor here in the rate at which we can create C molecules is the rate at which A is being transported across the membrane. Okay, now. So Randy says, can you show how to count molecules in site, but not in the other volume site, and O1V and O2V? Okay, so let's do that. Let's do that. That was the thing I was alluding to over here that wasn't going to work right. Okay, so if this is a little bit more advanced, but since Randy's asking for it, I'll show it to you because you should eventually be advanced enough to know how to do this. So to count this observable, we need to have a more direct way of typing it in. An explicit way, rather than having these, these buttons. Some observables are too complicated to specify with just a set of buttons that you click on. So this is where we need to make a new observable, and the type of observable is going to be, so we can count reactions, and we can count molecules. And we can even have observables here that come from a file that you can specify, and it's just a file that contains some data that you want to include in your graph. This is like a way to include external data in your graph. Data that maybe didn't even come from the simulation, but you still wanted to include it in the graph for some annotation reason. But the other one that we want to use here is this one called MDL string. And at some point, probably pretty soon, we're going to change this to be like a real BioNetGen observable specification syntax rather than, so MDL stands for Model Description Language, which is the old language that we used for programming MCell that wasn't based on Python. It was its own language that we invented. And we still have some pieces of it hanging around here in the interface, and this is one of the places. So I'm going to type in MDL string for this one. And the string, well, first of all, and it needs, first it needs a file prefix. This will be the name that is given to the file. And so this one might be, we might call it C site. And so the file on the file system will be called csite.dat somewhere. We haven't looked at where all the files that are being generated here are located yet. We'll do that before we end today, so that you're aware of it. And the files will be called, the files for this observable will be called csite. The files for these other ones are automatically named, like b.world and c.world. That's how they're named. You'll see it. But for this one, since this is a string of arbitrary construction, there's no good way to automatically name it. So we ask the user to name it. For anything in here, I'll just make a comment. For lots of the different things in this interface, we have what we call a description field. This is one. A description field where you can make a comment that describes exactly what all these different, exactly what this reaction is about. You can write a description, and that becomes a comment that will be included in the Python program that's generated, and you'll be able to look at it. But it's also a comment that you can see here in your CellBlender file. So you have the reference in both places. Okay, back to the plot output. Okay, so for the MDL string, we type count in all caps, square bracket. I think it's a square bracket, yeah. And then we're going to type in C, the molecule C, and where are we going to count the molecules of C? We're going to count it inside the site in the compartment called site, but not inside. If we just say the compartment called site here in the syntax the way it is here, where's my cursor? Ah, there it is. It was kind of invisible. I'll hit enter there for a second. So this isn't complete yet. In the old syntax that we had here, and it's documented on the msol.org website in a PDF document called the Quick Reference Guide. All the syntax for this is documented there. In that old syntax, the way we thought about these compartments was, if I say site, it means the entire interior of it, all of it, even what's inside its children, okay? But in BNGL, the compartment called site is only the volume not including its children. So how do we? But because we define this as the entire volume, including the children, how do we specify that we want only the part of this that's inside site, but not inside the its children? The way we do that is we can say, we can name the compartment, but the compartment is called, in here, it's not called site, it's called scene.site. The reason it's called scene.site is because this site is part of this thing called the parent of the whole model is the whole scene of your Blender model. And so we have to type in scene.site here. I think we say scene.site, and then we say all, which is the whole thing, minus scene.01v minus scene.02v, like that. So it's a little bit complicated, and I can probably copy that and paste it in the chat so people can see it better. Oh. Copy. It didn't paste for some reason. It's not pasting. I'm sorry. I don't know why it's not pasting. It's really weird. I can paste it here. No, it won't even let me paste it there. What's going on here? The whole world has gone brain dead. Ah, I see. I was clicking too many times. Ah, there it is selected. That's why. The indication that it's selected looks different. There it is. And I got it too. Okay. Raquel beat me to it. Good job. But it has to be the all. I'm sorry. Yeah, I missed saying all here. Yeah, I made a typo in it. Hold on. Here's a small typo in it. This is square bracket minus scene O2V square bracket all. Like that, copy.
Yeah, Tom, I just tried it and it doesn't like the scene dot. It should be just,
Oh, really? Are you
yeah.
sure?
It's,
Are you sure? Yeah.
yeah,
Okay. Well, that makes it easier.
I posted the string to chat.
Okay.
Yeah, this, oh,
Uh,
okay. Almost erased.
oh, that's surprising.
Yeah, that's some
Ah, that's very surprising. Okay.
real differences between MCell3 and MCell4.
Okay. This is a good difference. I like this difference. You can see it's so new that even the old creator of the original doesn't know how to use everything in it yet. So Adam's our new golden expert on all this. Okay. So I'm going to save. So if I have that, then so you can see what this is doing is it's taking the set of points in space represented by all the cytosol and subtracting off the space of O1V and O2V. So this is basically kind of what's called Boolean operations or constructive solid geometry operations or set operations, Boolean set operations, where site means the set of points and all means the region that includes all of it. And O1V all minus O2V all. This set minus this set minus this set. What remains? This is what's called a Boolean difference operation or Boolean difference set. So what remains is the set of points that are outside of these two, but inside of this one, right? And so it'll be just the cytoplasm proper. Okay, so if I do that and save that, and then if I run the simulation, and it looks like it's gonna run without error. Yes, there it goes. So thank you, Adam. That was indeed right. Reload that and let's generate our plot. Okay, there we go. So it's hard. I'm a little bit colorblind, so it's hard for me to see all these colors, but this one here appears to be maybe what color is that? Is this one here, I think. So C inside of O1V, I think is this one. And some of them, which is greater than the ones that have been transported back out into the world. Of course, that should always be the case because C is created inside of O1V. And so the amount in the world should always be less at early times when C is still being created. The amount in the cytoplasm should always be less than what's inside the compartment where it's being created. There'll always be a lag at the beginning. Okay. Okay, so that's working. So now to finish the model, what we're going to do is make another transporter. And what we're going to do is we're going to sequester the molecules of C inside of the second organelle. And when we do that sequestration, we're going to convert the molecules of C into a new molecule called D. So again, whatever this molecule of D is, C is safe to be sent back into the cytoplasm, but we need it in the creation of another metabolite called D that is necessary inside this organelle. And for some reason, we want to keep it compartmentalized so that it's isolated from the rest of the cell, because maybe it's dangerous, or we want to concentrate it and have it at a high concentration. And by having a small organelle in which we create it, we can create a high concentration of that substance, right? And have a high mass action kinetics way of operating it. even when we have small numbers of D. So if we have small numbers of D, but we want a high concentration, the only way we can do that is to put it into a small compartment. So this gets us thinking about, the kinds of things that can, that can happen in cells where they, are able to have, ways of creating small organelles and having enzymes that operate inside of small or large organelles and operate with, high concentrations but low numbers of particles, right? This is what cells do. Okay, so one thing that Terry likes to say about these kinds of things is that they look disorganized, but they're really organized, right? So it's kind of, reaction diffusion gives you, and spatial reaction diffusion gives you a way of having something that's organized and disorganized at the same time, which is kind of fun to think about. Okay. So now we're going to have our molecules of, we're going to add a new transporter called T2. That's going to be a surface molecule, and it's going to have a diffusion constant, say 1e minus 9. Let's make it move. Let's make it move, even more slowly, just for fun. And then we're going to add another molecule called D. Our last molecule is going to be called D, and it's going to be a volume molecule, and with a diffusion constant of 1e minus 6, say. Okay, so there we go. And now let's make our reaction, a new reaction, where we're going to say, C at out plus T2 goes to D at in plus T2. So this is the reaction where transporter 2 is going to move C from the cytoplasm outside of the organelle to the inside of the organelle. And when it does so, it's going to convert C into D. And so I'm taking some shortcuts here in writing these reactions. We're doing this without, using components in the BioNetGen language, and we're not making intermediate states in our reaction complexes that we're making, but that's okay for this toy model. Okay. And our rate constant for this is going to be 1e8. No. Yeah, 1e8. That's correct. Okay. So now all we need to do is put T2 onto O2V. In our molecule placement, we're going to make another release site where we're going to say at O2M colon T2. And this is going to be a object region placement. And we're going to name O1, O2V square bracket O2M. So this syntax, to remind you, means the O2M surface region of the object called O2V. Okay, and the number to release there is going to be 700. Okay. And then in our plot output, let's count one more count statement, which is going to be the number of D molecules. We can say in the world, but just to be fancier, the only place they can be is inside, O2V, but we can say D in the object called O2V just to be explicit about it. Okay, and now we're ready to run the simulation. I'm going to save it. I'm going to clear. I'm going to say export and run. Okay, it ran. And I see Ania asked, do we need a reaction to convert C into D? And yes, we do, but we already made it. And we did it all, we did the transport and the conversion all in one step. We C at out bound to T2 or interacted with T2 and irreversibly resulted in a product D at in plus T2. So there we go. Okay, so I'll say I'll clear that. Well, we already ran it. There's our new result, and I can hit play, and it goes. And another way to move time here is you can grab onto this time indicator, and you can pull it along and drag it. And I'm not seeing any D molecules. They should be yellow. They should be yellow spheres. Let's make them yellow cubes. Oh, I know why. Okay, I know exactly why. So we're only running for 1 millisecond of simulated time. To see more things happen, let's change the number of iterations from 1,000 to 10,000. And so now this is going to run more slowly, but don't hit run yet. Maybe some of you already did. You can hit kill and kill it. Because what we're going to do is I'm going to go into here into this partition settings, and we're going to say automatically. So what partitions are imaginary planes that chop up the world into sub cuboids, and what MCell will do is calculate within each cuboid only the collisions between other things within that cuboid. It's a divide and conquer strategy. It doesn't change the result of the simulation, but it changes the speed of the simulation because it makes the collision detection more efficient. And I can explain more about that. Here, it's going to go from minus 0.625 to plus 0.625 in all 3 dimensions, X, Y, and Z, in steps of 0.1 microns. And a better step size might be 0.05. That might be a better step size for this simulation. And now we're going to say export and run. And it's going to run faster. And maybe some of you have been looking at the console output of an MCell run. I should have been doing this earlier, but you can see over here what iteration number it's on and how many iterations per second it's going. And you can use this iterations per second as a tuning parameter for your partitioning to find the sweet spot for making the partitions. Because there'll be a point at which the speed up is as much as you can get. And then if you go to finer partitions, it'll start to slow down again. Because the partitions themselves also have to be calculated in the ray tracing. Okay, so there we go, but it ran pretty fast. Mine ran in 30 seconds for 10,000 iterations. And now I can go to the plot output and say plot it. Okay, and there we go. So now we can see over a 10 millisecond simulation that the number of C molecules inside the organelle reaches a peak, and then it starts to go down again because we're transporting them out into the cytoplasm. Here's the total amount of C that we've created in the world. And then, oh no, this is, I'm sorry. This is the amount of C in O1V, and this is the amount of C in the cytoplasm here, always lagging until, until we pass the peak, which we haven't yet. Then they'll catch up. And then it'll start to go down again because the C is being transported into O2V and being converted into D. And that's what's shown here on this line. This is the amount of D that we've created so far in the simulation. And because all our reactions are irreversible, eventually every molecule of A and B that can react will be converted into a C and then a D. So the total number I said before, because A is an excess, would be 1,000. So eventually we'll get 1,000 molecules of D. We can see by this point in the simulation, at 10 milliseconds, we've only created 280 or so of D. So we're only about 1/5 of the way there, or a little bit more than 1/4 of the way there. Okay. And now, if I reload my visualization, now you can see I have 10,000 time steps to look at. And there's our molecules of D being sequestered into the organelle at the very end. Okay, so now, what time is it? It is 4 o'clock, which is kind of the official ending time. But if people can indulge me just a little bit more and can stay just a little bit more, we can, let's see how many people are still on today. If that's okay with you. See how many people are still here.
23 in total.
Okay, 23. For some reason, I can't see that number in my Zoom interface. I don't know why. Okay, so that's most of us. I promised to show you how we can import, make this a little bit more spatial, and also how we can import a model directly from BNGL, and also look at where the files are located from this. So I think if we have just a little bit more time, we can do those last few things. So what we have created here is a model that has the transporters uniformly distributed over these two organelles. But what if the transporters were kind of spatially localized on different parts, on specific parts of the organelle? For example, since the transporter T1 is transporting C molecules out, and the transporters T2 are transporting C molecules in, these two organelles are right next to each other. But what if their transporters were spatially organized to make like a little mini synapse kind of structure, where the T2s were concentrated here and the T1s were concentrated here? What would that do to the simulation? So first of all, before we go there, I'm going to do a save copy rather. This is our milestone. This is really our milestone 5. Which I purposely didn't save yesterday because I knew we would get there together and have this. So this is our milestone 5 right here. I think that's correct. No, this is really milestone 4. So this is the same as milestone 4. So I'll do save copy and I'll call this one milestone 4. But it's our one that we made today, but it should be pretty similar to what you have on the website too. So this is pretty much the same as milestone 4 on the website. Okay. one difference might be this new reaction here. So maybe I'll call this, save copy, maybe I'll call it milestone for A. Or I could call it RS for Randy Stout, ARS, because it was Randy's idea to put that. Okay. So this is model organelle demo milestone for RS. Okay. Okay, so now what we're going to do is we're going to hide. We're going to go to the model objects and we're going to hide the cytosol. And we're going to pick O1V here, and we're going to go into edit mode with the tab key. And we said that region O1M is the whole thing. But let's change that up. So what I'm going to do is, first of all, maybe unselect everything, and then say select. So choose O1V in the list of regions. Of course, there's only one region. Or actually, let's keep it this way to keep it simpler. What I was going to say is we can make another region and put T2 only in that other region. But if we did that, we'd have to edit other parts of the model, and it's where we already said O1M for those things. So let's keep it simpler, and we'll actually change the structure of O1M. Okay, so pick O1M in the list of regions. Say select to make sure it's all selected, and then say remove. So what this is going to do is it says remove selected spaces from the region. So if I do that, those spaces are no longer members of the region called O1M. And to prove it, I can say click outside this and then say select O1M, and now nothing happens because right now O1M is an empty region. And I think MCell is not happy if you try to run a model with an empty region. So be careful about making empty regions. We might want to consider making that be a warning condition rather than an error condition. I don't know. Okay, so now what we're going to do is maybe orient our model so that we're kind of looking at it. And we can see that there's some faces here, a set of faces here that are close to O2V. And what I'm going to do is I'm going to shift click on those faces. And just for a moment here, let me stop that. I'm just going to click outside this. All the molecules here are kind of getting in our face and making it hard to see. Let's go into the molecules control panel. And what I didn't show you earlier is that we have control over the visibility of the molecules, and including visibility over all the molecules. So I can click on this button on the right side of the defined molecules list, way over on the right side. That looks like a closed eye, and that will hide all the molecules. So don't forget you did that, because you might be confused. Why am I not seeing the molecules in my simulation? It might be because you've hidden them all, right? So there's one for hide all, one for show all, one for a button for turning on and off individual ones individually, and then the magnifier glass is a shortcut for show only. So if I want to show only the B molecules, I can click on the magnifying glass, and you can see what happens here is it turns off everything else and turns on only the one that you select. So this is really a useful thing. So if I want to look at just the D molecules, there they are. Hide all. If I want to look at just the D molecules, I click on the magnifying glass for D, or just the B's, or whatever you want. Okay, but let's hide everything. Okay, so now focusing back on our job here, let's shift click on these faces of O1V that are facing closest to our O2V. And after we select them, then over in the model objects control panel for region O1M, we can say assign. And then I can say deselect, and you can see there they go. So now I've got those faces are the only faces that are members of O1M. And MCell doesn't care that this surface region is not the whole object, right? Whereas the way things work in BNGL, the membrane compartment means the entire membrane of that compartment, and it does not mean a subsurface of that compartment. Okay. But really, you know, in BNGL, compartments aren't three-dimensional. They're really just point compartments that have a volume parameter that you give it and a surface area parameter that you give it. So you could say that the volume is this whole volume, but the surface area is only a tiny surface area of that volume. Now that seems to imply a certain surface area to volume ratio, but it doesn't have to mean that. It can mean the volume of the compartment is this, but the surface area that contains the reactants, you know, the enzymes, is only a small fraction of the surface area of the whole compartment. And all you're saying is, no, its surface area is this small surface area, right? And that would give the correct result, the expected correct result in BNGL if you ran the simulation of that. Jim's not here, but I'm pretty sure what I just said is true. Okay, so there we go. We've got O1M specified as this small patch. And now let's get out of edit mode. And now let's select O2V and, O2V, and rotate this so that we're looking at it. Oh, I don't know why I'm biased about looking at things from this side, but I kind of like looking at it this way. And now let's select some of the faces over here. And maybe what we'll do is we'll look straight down the pipe from the point of view of O1M, I mean O1V, and I'll select O1V. And I think what I can do is now with O2V selected, go into edit mode. It looks like everything is hidden here, but I think if in O2M, if I say select, yeah, it doesn't light them up. They are lit up, right? But they're being hidden, right? Look at that. So that's pretty confusing. So let's do this. So I'm going to get out of edit mode. I'm going to select O1V, but looking at it from this point of view, looking straight in, so I can tell where the faces are that I'm going to select. Go into model objects, select O1V and hide it. So now we're looking at only O2V. So select O2V in the list. There's O2M. Go into edit mode. Make sure everything is selected and then say remove. And then click outside of that. And now let's select some faces that are in line with the contact proximity with O1V. And we could shift click on these like this and keep going and shift click, but that's a little bit slow and tedious. I'm almost done, but I'll show you how to do it another way here. Let's say these are the ones I want. But another way to do this is, what if I click outside here and make those go away? I can hit the C key on the keyboard, and this gives me a circle select tool that I can control with the middle scroll wheel. I can control the size of that. And with that, I can even, left click and drag and draw like a spray gun, right? And if I hit enter, then it accepts that. Now that's not what I wanted, but I just wanted to show you how you can do that. You can even do things like use the C key, and I can even do this. and kind of make a smiley face or whatever. You can do crazy things, but really this is all about selecting the anatomical region that you want with maximum flexibility, right?
Otherwise, Tom, Michael found a good point that these surface regions, when they have the same name as the BNGL compartment, as the surface compartment, these regions must cover the whole surface. Otherwise, we need to use a different name. So, for example, here it can be like X. Or
Oh, I thought we, Adam, I thought we had fixed that.
Yeah, apparently not. Or this is, I don't know, intentional, so that it does not get confused with the BNGL compartment, because it's not in fact. But yeah, we can.
I think it's necessary for the reason that I said a moment ago. I think it's necessary to allow it, even if it isn't the whole thing. I think it's still we can go over this with Jim at some point, but I think it should be allowed.
Okay.
Yeah. Because in I didn't realize that until I was explaining it just a moment ago, that it could be the case. It could be the case that I have a volume, and the molecules that I want to place are only a part of the surface area of that volume, right?
Okay.
Even in BNGL, right? And I might want to be able to do that. I don't know.
Mm-hmm.
Yeah.
In fact, yes, you are right. The simulation result will be the same because the concentrations will be the same.
Yeah.
Okay. Yes. Okay.
Right. See, do you see? Yeah. Because the concentration on the surface becomes a surface density, right?
All right.
Okay. Anyway, so I'll hit enter there. I'll undo that. I'll use the C button here, and I'll draw. I'll draw just those. Let's say that's the patch that I want. I hit enter to accept that, and then I hit assign to assign that, and then I should be able to hit select and see that it's true. Okay, there it is. But I guess Michael's saying that they have to have a different name. Well, let's cross that bridge here in a moment, because I thought I had tested this even and got it to work. I don't know. Let's see. Find out. Okay, so then I get out of edit mode. Let's see, edit mode. And then I go back in here and I turn on my objects. There we are. There's our objects. And then I can go into the molecules and turn on all the molecules. And then I would have to run, let's do a save. And let's do a run simulation. And let's see if it complains. Yes. Okay. Okay. So yes, indeed, that is a bug, or I guess a feature, right? For now, it's a feature, and we'll change our policy about that pretty soon. Okay. And what does this say? Would lead to inconsistencies? Well, I don't know. Maybe not. Maybe it wouldn't. We have to think about this and study this. It might. Yeah, this might be correct. I don't know. We have to study this a little bit more. Okay. So, but in the meantime, what can we do? What we can do is, in our molecule placement, maybe for now, right? Would this be okay, Adam? For now, I can just delete that.
Right.
I think that'll work, right?
Yeah. And then in the object region, we need to change the
Ah, we had,
and O2M something.
or, yeah, change the name of it there. But back over here, I would keep these names the same because these aren't even going to be used, right? These,
Yeah, the compartments can stay the same.
right. Okay, all right.
Yeah, only in the defined surface regions. We need to, yeah, on this,
Yeah.
on the bottom.
Yeah, down here. So, so I'll say O2MS maybe might be the name of that one. And then for O1V, I can call it O1MS for small. And then here, we don't need to change the names of these because we're not going to use them. In the molecule placement, we're not going to use for T1 and T2. We're not going to use those names, but for the name of the region here in the object region where we release on it, that's where we put O1MS and O2MS. I think that'll work. I know this is confusing and I'm moving fast, but let's see if this works. Ah, okay. This is T2. Okay, I think what this means is the region we put on T2 is too small to fit the 700 molecule that we want to put there. Okay, what does this mean? So I said earlier, I'm glad we had this error. I had said earlier that that surfaces are subdivided into little effector tiles of a certain area, and that area is the collision cross section for calculating the reaction diffusion there, and so there's a maximum packing density for those effector tiles on the surface. And if you try to pack more molecules than will fit on the surface within the region that you've made, you get this error. So what we can do is is to make that region bigger for the T2s. Okay, so what we're going to do is go back into the model objects, and we're going to hide those. And again, hide the molecules so we can see what we're doing. And go into our model object for O2V and go into edit mode on O2MS and say select it. And there's our region. And what we're going to do, I think, is just use the C control again and expand this by 1 rim like that. And that's probably big enough. And then I'll say assign. Okay, and now get out of edit mode, go back into the model objects and turn on our 2 objects, go into the molecules and turn on our molecules, zoom out. There's our object. And now we can say save and run the simulation again, clear and run. And now it's happy. So there has to be enough room to fit the 700 molecules we asked for. And I'll show you in a second where we control the density of that packing on the surface. And by default, it's set to 10,000 particles per square micron. So that means imaginary tiles that are about 100 square nanometers, or if they were little squares, they would be like 10 by 10 nanometers. So about the size of real proteins in the cell. Okay, so there it is. And if I say reload the visualization, now we can see If I go back to time 0, now we can see there's our little patches of receptors on the surface. And if I say, and we just ran it, I'll move this off to the side. And if I say plot the output, whoa. Uh-oh. What's going on? Oh, there's my mouse. Okay. Uh-oh, something's happening. Oh, okay. There we go. Plot output. So there you go. Huh. This is Zoom interfering with my world. This is Zoom interfering with my world. Okay. Zoom took control of my universe here for a second. Okay, plot output settings, plot. And here's our new result. And here's what we had before. Huh. It looks identical. That can't be right.
Maybe you have more figures there somewhere.
Oh, yeah. Maybe that's it. Maybe it happened twice. That looks the same. All right. What do we got? I think I was clicking on the button a bunch of times, and I got a bunch of copies of that. I think that's what happened. Ah, there we go. All right. So this is the old, and this is the new. And so we get a different result in the new one, but it's not clear that we made the impact on the system that we wanted to make. But certainly we got a slight difference in the outcome due to the spatial localization of those. Looks like it got less efficient at creating the C molecules, which are these two curves. So somehow this arrangement is less efficient at creating the C molecule, which is this upper curve. And we'll have to think about why this arrangement would be less efficient. And it might be because when the C molecules go in between here and get transported in, we create a small spatial gradient here, or a deficit of C molecules in this vicinity, because what we've done is we've made the density of T1 molecules higher. And so they're going to be a bigger sink on the C molecules. And by being a bigger sink, we'll get a gradient here. And that gradient will cause a slightly lower concentration of C molecules in the vicinity of these T1s. And that will decrease the efficiency of their transport. So I think that's probably what just happened. And why we're seeing that difference. Okay, so I will save this as milestone 5. Save copy. This one really is milestone 5. And if we run this, we can see that because we have a diffusion constant on T1 and T2, the molecules T1 and T2 start inside their little regions, but they slowly diffuse away from there. And if I pull time forward, you can see they're diffusing away from there. But even after, I guess, even after 10 milliseconds of simulation, they're still, relatively concentrated near their starting point. Okay. So let me just quickly show you where the model, when it ran, output its information, and then we'll import the BioNetGen version of this model into here and just show you that you can do the import. Is that okay with people doing this at 4:30? Just a little bit more. People still have some stamina. I know we've lost a few. This will be in the recording for people who aren't here. But since I promised to do it earlier, I better do it. Okay, I see people saying yes, so let's go. All right, so this model is called organelle-demo.blend. And when I save the model, if I do save, let's say save as, this model is being stored in my directory called users Bartel CMW 2021 organelle demo 1. Okay, so what I'm going to do here is in my file system, let's see, over here. I'll do it right here. In the file system, I've already CD'd into that directory, and you can see it here. If I clear my screen so that you're not confused, if I type ls here, you can see here's the blend file for it. Here's our milestones that we made today. And this file called blend1 is a backup blend file in case something got corrupted. This is like an auto save backup file. And then when we run Blender using the export and run button, CellBlender creates a subdirectory automatically in the same folder as where the blend file is located. And the folder is called the same as the file name, organelle demo, but with underscore files appended to the name. So if I cd into organelle, sorry, organelle demo files, if I cd in there, you'll see there's some stuff here. There's a timestamp that lets CellBlender keep track of when the last time was you ran it. And so it can keep track of when things need to be updated. As you make changes to your model, this is like a timestamp that it uses. And then there's a subdirectory called mcell. And the reason why we make a subdirectory called mcell is we envision someday someone with CellBlender might want to model in a different simulator besides mcell. And so we would have different subdirectories here for different simulators that were used to run the model. Okay, so under the mcell directory, there's a JSON file that we don't need to talk about that describes the data layout of the information that's inside the output data. And the guts are in the output data directory. If I type ls here, we see the model in its Python form. There's a vestigial file here that we probably don't need to be exporting from CellBlender called scene.main.mdl. You can ignore that one. Your model, the main part of your model is in a file called, I'm sorry, scene-model.py. Scene-model.py is the main module of this Python program. It's where the main routine is located. And it's where this is the file that you would execute in Python to run the whole model in mcell from the command line. Okay, and I won't show you how to do that here. This is what Adam will show you on Thursday. But what I wanted to show you is you get a file called scene-model.bngl. This is the BioNetGen language form of the model. And if we look at that, you can see it starts with a warning. It says this is an automatically generated file that will be overwritten by CellBlender on the next model export. So this is your warning to be careful with this file. If you make any edits to it, don't save the file here. Move it to a different place where CellBlender won't be overwriting it. And then we get some nice comments in the file, and it has a parameters block, but we didn't make any parameters in the model, so that's empty. We have the molecule types. We have the compartments with their volumes and their names and their dimensionalities and their containment. For some reason, O2V is missing from here. I don't know why.
That's weird.
Yeah, okay.
So-
Well, you know,
Sure that you have the right directory. Because this.
oh, don't do that. Okay. Oh, yeah, this should be, let's look at the time. These were made at 18 after 4 o'clock, so these were made just a little while ago.
Okay,
Huh.
so maybe I'll have to check.
Huh, okay. That's really odd. Okay, but anyway, I wanted to show you that you have the BioNetGen language file here that has the reactions and the observables. These aren't all the observables. Huh, okay, maybe it's only the observables that it knows how to deal with. Some of them were a little bit fancier. I'm not sure. But okay, but the output from the file, the output from the model is created in a subdirectory here called React data. If I cd into React data, there's a subdirectory for each seed of the model that you run. And we only ran one seed for the random number generator. Now this differs from how things are done normally in BioNetGen, where, well, if you're running an ODE, it's not stochastic, so there are no seeds. And if you're running with with the SSA algorithm or the NFSIM algorithm, which are stochastic, you can specify a seed to the random number generator. But Jim can remind us how that's handled. But if I cd into the seed directory, then you can see here I have the files that I told you about. We have A in the world, and A in O1V, and B in the world, and C in O1V, C in the world, D in O2V, and then remember we asked for C site, which is, and that was the name that we gave it, and there it is. That was the prefix that we asked for, and so we know what's in that file. So, and there's a new option in MCell that Adam will show you on Thursday, where you can ask for the output to be generated in a format compatible with BioNetGen, a GDAT file that you could then load into the Plotly plotter in the BioNetGen language extension of VS Code. And so on Thursday, Adam will go into more detail about creating models, Python models, and how to run the Python models directly. But what I want to show you right now is the very last thing. And of course, yes, you can do all this in a Jupyter notebook. I'm not sure if Adam's going to demonstrate this in a Jupyter notebook or not. But Adam will show you his preferred way right now of making the models. Whether that's in VS Code, I'm not sure. Maybe it is.
Yes, in VS Code.
Okay, very good. Thank you, Adam. And if I go back up to this top level directory, then I have a version of the organelle model called the organelle transport model. And this is the version of the model that Jim showed you yesterday in this file called organelle transport BNGL. .bngl. This is exactly that file that you were looking at, with a few modifications that allow it to go back and forth between BNGL and MCell. And Adam will talk more about this on Thursday, but you can specify some constants that start with a keyword and then the name of a variable at the end, which when you import this into CellBlender, CellBlender will interpret these things and set these values in the CellBlender user interface for MCell. But since these are not used in the BioNetGen version of the model, these are just ignored. These are defined in BioNetGen when you run it, but they will not be used. They'll just be meaningless or degenerate parts of the model from BioNetGen's point of view. And here you can see we have the compartments and the molecule types and the reaction seed species and the reactions, just as we just made them in CellBlender, with the difference that we don't have the in and out keywords in the language in BioNetGen, in pure BioNetGen language. That's a special extension that MCell has. So in this version of the model, we have the currently supported version of how to deal with the compartments, where you have to name the compartments and the motions of transport explicitly. Okay, so now, how would we use that model in CellBlender? Let me show you. This will be the last thing we do today. So let's see. So over here, I could say, let's just make a new model. I've already saved this one as milestone 5. So I can, since it's milestone 5, I should SCP that somewhere back here. I'm too lazy to do this another way. I'm going to SCP milestone 5 over to our location on the file server, so you guys can have it and grab it and play with it. And so, okay, so now what I can do is, in our model, go to a new blank slate. See, let's make it really a blank slate. And let's see, I think you should have a copy of that file called organelletransport.bngl in that location on the file server. So if you downloaded that file, you could do what I'm about to do. But in the interest of time, let me just do it. So in the file menu, I would say File, Import, Compartmental BioNetGen Model. And you can see here, there's 2 different BioNetGen related options in the menu. And one of them, the first one, called BioNetGen SBML model, we're going to do that in conjunction with the Cell Organizer tutorial, and probably cover that on Thursday during their advanced topics of Cell Organizer, where there'll be a model that's generated in BioNetGen SBML syntax format, generated by Cell Organizer, that contains geometry generated by Cell Organizer that we'll be able to import into CellBlender and use as the geometry for a model. But what we're going to do right now is this second one, which says compartmental BioNetGen model.bngl. So if I choose that, then I get a navigator, file navigator, and I can navigate to the directory where I have that model. So navigate to wherever you have it and choose it, and then say import CBNGL model. CBNGL stands for compartmental BioNetGen language model. And if I do that, it imports a model. Now this doesn't look like our organelle, our site with 2 nested organelles because they're not spheres, right? Or subdivided icospheres. They're little boxes. But topologically, this model is identical to that other model. And the only information about these compartments that were in that BioNetGen language model, if I go back to it, organelle transport model. The only information we have is up here. There's some variables that define their volumes up here. And then their names, the compartment names, their dimensionality, 3 or 2-dimensional, meaning volumetric or surface, and then their volumes, and then their parent and child nesting and sibling relationships specified here. And from that information, the importer was able to figure out how to make a box of a certain volume in some compartments of certain volumes. Now, I think there are some issues with creating compartments of the right volume if there are sibling compartments, as we have here. And we'll figure out how to deal with that issue in future updates to this. But topologically, the model is created correctly. And if we look into here into the CellBlender panel, we'll see that this model has imported and has come with all of its parameters. It has come with all of its molecules, surface molecules and volume molecules. Now, this version of the model is slightly different because the reactions have, in this version of the model, we made the reactions so that they have intermediates. So that when, say, when A reacts with T1, there's a reversible reaction that creates an intermediate called AT1. So that's a slight difference in this model, but it was just in the way that it was created. And the rate constants now, instead of being hard-coded in, are specified directly as parameter values. And these named parameters are in this parameters block of the model. And we can see them all in here. Here's our KP1, KP2 reactions, and the value of the rate constant is shown here. And so there's the model. And then I could go in here and I could specify the number of iterations for the model. One thing it doesn't know is how to set the number of iterations. So you do that yourself. And it can't really come up with a good guess for how to do that because iterations is not a time unit. It's a number of iterations and a time step. And the model that we imported, I think did not. I think it had an actions block with a start and end time and a number of steps. And probably we could have parsed this and pulled it out, but I'm not sure that our importer parses the method section to set up a similar iteration and time step over here. Of course, the MCell time step needs to be what it needs to be and is a separate, in the sense, this part of the user interface here this is like the actions block of the BioNetGen language model. This is controlling the physics engine and the parameters for the solver that we're using here. Okay, so we can set that. I have to save the model because I haven't saved it yet. So I go here and I say save as, and I'll save this right here, and I'll call it organelle demo. I'll call it organelle transport, maybe imported .blend, save as, and then I can say, go into the run panel and say run, and there it goes. and I can load it. And so there it is. Now the glyphs and everything are generated automatically when we imported it. So if we wanted to change the colors and all that stuff, we'd have to go in here and control our colors. So the colors aren't going to be exactly the same as what we had. And the model is a little different anyway, because we have these intermediate steps in the model. Now at this point, I won't show you how to do this right now, because on Thursday, we're going to be doing it with Cell Organizer. At this point, what I could do is replace each of these compartments with the spherical organelle compartments that we made in the other model. And I think on Thursday, I might have a chance during the Cell Organizer session to show you how to do that. Plus, it's now 4:45 and getting a little late. So maybe you guys are burned out and tired like I am. So maybe this is a good stopping point, and maybe I can take questions from people before we end for today. Thanks for sticking with me, you guys. You're really troopers. Okay, somebody say something.
There was one question from Lenka. Three questions before.
Okay.
Just could you model immature tripartite like the organelle model we created today?
Yeah, that would certainly, a model like this is certainly a kind of a good kind of scratch pad or a foundation piece to start from to make a model like that. Absolutely, that could be done. And I think hopefully, Lenka, it was clear in my lecture earlier today when I was showing the dendrite and axon and astrocyte model, that with the way that's all put together, there are certainly places within that 3D structure of the neural pill where there are tripartite synapse structures within there that could be a focus of a simulation.
Maybe Randy, you had a question. I'm not sure if I answered it correctly in chat.
Okay. So what was Randy's question? I see your answer to it.
This import does not work with regions, right?
Right. So let's look at the model objects and the imported model. So in the model objects, we have the parent. I'll be right there. Okay. Wendy's giving me the 10-minute warning for dinner. Okay. So we have the compartments listed here, and if I pick one of these, you can see that there were actually regions made on O1V and O2V, but these regions are the entire object and not a subpart of the object. So we do have the concept of region, except it has to be the entire object. And that's because we can double check with Jim, but I think that's how it's conceptualized in BioNetGen, in compartmental BioNetGen language. And unless they have a way of bending that definition or augmenting that definition, if you're in BioNetGen language with ODEs or SSA or whatever, that's the concept that you're stuck with. That the plasma membrane of a volumetric compartment is the whole thing, and they do not have the concept of subregions on the surface of the object. And of course, it's hard to think about in a compartmental model where the compartments are really well mixed point compartments. They're not really 3D compartments. There's a tendency or a desire, right, to try to think of it that way, but really mathematically, it's not at all a compartment with any number of dimensions, right? Even though you say 3-dimension or 2-dimension, that's really just a definition of how to think about the space unit or the length unit or the area or the unit of area. That's all it is, right? But only when you come to real 3-dimensional space like we do here in CellBlender and with MCell, can we think about other ways of thinking about the compartmentalization. And I'll maybe close with that it's possible to make these compartments in MCell and CellBlender. It's possible to make these compartments transparent to the diffusion motion of one kind of particle, but reflective to other particles. And you can also make these surfaces absorptive to particles. You can make surfaces that emit particles at a constant rate, simulating that simulating a concentration clamp. You can and when I say compartments, I mean not just 3D compartments. You can make 2D compartments on the surface whose boundaries, which are aligned, are reflective to particles and keep the particles corralled within them, and they can be a corral to one kind of particle, but transparent and let other particles pass through, without impediments, right? And so just like you have 3D boundaries, a surface is a boundary of a 3D volume. A line on a surface, a closed line on a surface, is a one-dimensional boundary to a two-dimensional area, right? And so there's this idea of simplexes and manifolds and things in different numbers of dimensional space. And this is all encapsulated here. And someone said that the lipid raft, did someone talk about the lipid raft? No, okay. So we've tried to capture in MCell and the specification of surfaces and volumes and regions in MCell concepts that are universal and useful for creating any kind of model that you might imagine. So maybe that's where we should end it here. And if there's a few more questions, I could answer those.
Tom, I have a quick question. So,
Sure.
So let's say if you have a kind of a topography of either EM, electron microscope, let's say a scanning electron microscope, or even fluorescent microscopy that you cannot obviously figure out, let's say even of a lipid raft that you just mentioned, for example. So you'd be able kind of regenerate that in 3D model based on that image. Am I correct? Am I going the right way on this?
Yes. So Cell Organizer is one tool that's from our team members of MMBIOS, Bob Murphy's group, and you'll learn about that tomorrow. Cell Organizer can take fluorescence microscopy images and other kinds of images, but their main focus has been, and main clientele or collaborators from the community, people who mainly use fluorescence microscopy images, but I think Cell Organizer is more general. It can be any kind of image modality. But from those images, Cell Organizer can generate what's called a generative model of the parameter space of the surface of the objects in those images. from those generative models, you can sample the parameter space and create instances of models that could have come from those distributions, and you can instantiate those models as 3D surface molecule models that could be imported into CellBlender and used as the framework for a biochemical model.
Awesome, thank you. Because some
Yeah.
data cannot be seen, so that could be gives an additional hypothesis of
Sure.
how things are in real life. Thank you so much, sir.
Sure.
Really-
And then during my talk earlier, I mentioned that with Kristen Harris, we've collaborated and used EM images to make 3D reconstructions of dendrites and axons and astrocytes. And those 3D reconstructions were used to generate mesh models that we imported and created that whole model that I showed.
Awesome.
Yeah. So it's a little bit tricky and difficult to do, tedious to do, but it certainly is doable and worthwhile.
Yeah,
And
absolutely.
and we're trying to by making these tools, we're trying to make this more productive and make a pipeline for it that's more cookie cutter and easy to do. And little by little, we're getting there. It's getting smoother and smoother every time we do this.
Awesome. Thanks, Tom. Appreciate it.
Sure. You're welcome, Dimon. Okay. I'm ready for my arrogant bastard. I don't know if you guys drink Stone Brewing. I like Stone, and I have an arrogant bastard waiting for me. Hope no one's offended by my use of that term, but so Adam, I think you're muted.
Yeah, that I'm waiting to open my Lagunitas API.
Okay, now I'm going to save this one again, and I'm going to quit from there, and I'm going to stop sharing my screen. And with that, I will salute you all for being, the best troops there ever were, for sticking with me this whole time.
This is a great talk. See you tomorrow.
Okay, see y'all tomorrow at 7:30. Okay, bye
Thank
everyone.
you so much, everyone.
Bye, thank you. Thanks,
Thank you.
Rosita. You're great.
Bye-bye. And
Bye.
before, please feel okay, it's just us. I was too late.
Yeah.
I will bug them with messages. Okay.
Yeah.
Thank you very much.
Okay.
Bye-bye.
Thank you. Bye.
Yeah.
Thanks, Adam.